If we're boring, you can talk about it. You guys are fine.
Hello, howdy.
Howdy.
Welcome to Astronomy on Tap. We are the astronomers at A&M, Duke grad students mostly, and we organize this event once a month so that we can keep everyone updated on what's going on in astronomy and also just teach the public about random astronomy things. So this is the 41st Astronomy on Tap, so and we do believe trivia, but we're not doing trivia today, so that's that. We might throw some astronomers up here and you can ask some questions. That'll depend on whether or not we want to come this year. So TBD. I am MC Blue Moon Skater Girl, and this is MC Justin.
Normally I'm Astro Man, but I guess out of my Justin. Yeah, like and subscribe to our YouTube channel. I think it's tx.ag/aotlive. Follow us on Instagram and Twitter at AoT_BCS and Facebook at AoT BCS. There's our website. We organize all our stuff on. That's the main website.
So to help support the Grand Stafford, you can Venmo Jose Quintana 20 and put Stafford Tip in the description, but also tip our wonderful bartender. And then you can support us, please, so we can keep the show going at AoT BCS. And if you donate $15, you get a t-shirt. So, yeah. And we also have some cool swag.
Okay, so tentatively, our next event will be December 22nd. We will make decisions later. That's the fourth. That's the fourth Wednesday in December. And then all the astronomers should have glow sticks. Astronomers who don't have glow sticks, they're back there on the table. So if you have questions during the event or after, feel free to talk to us. Yeah, we're always happy to answer questions.
Our first speaker of the night is Alex Riley. He is a PhD candidate at A&M, a fifth year. He has a cat named Brandon. His MC name is Dark Matter Dude, and he's going to talk about the decadal. Now, I'm not going to say what that means because he's going to explain what it is. I know what it is, but welcome, Alex.
Hello, everybody. I got my COVID booster shot yesterday, and so that's why I'm double fisting water and Gatorade right now. So yeah, we're going to talk a little bit about big dreams and big telescopes going over the next 10 years of astronomy. So if you pull a random astronomer off the street and ask them, hey, what are you working on? Like, what's the big question that you want to answer? You'll get a lot of different answers. Some people will say, I want to know how the first stars, galaxies, black holes formed. Some people will say, I want to understand this weird stuff called dark matter and dark energy. And even others will say, are we alone? I want to, is there life out there on other planets? And so all of these different science goals have particular wavelengths and types of telescopes that are good for answering those questions. And kind of one big question is like, how do we decide what gets built? How do we set priorities for astronomy going to the future? And the answer to that is something called the decadal survey. So that's what we're going to talk about today. The most recent decadal survey, called ASTRO 2020, just wrapped up and got put out. Basically, the idea is the National Academies of Science puts together a group of very top-shelf, high-level astronomers, and they kind of solicit feedback from all of the astronomy community, and then put out a big report saying, sort of setting out the next 10 or so years. This is sort of ASTRO 2020 by the numbers. There were 860 white papers submitted. So that's 860 instances of a group of astronomers getting together, writing a paper saying, hey, I think X, Y, Z is important, and sending them off and getting it submitted. 573 of those were science papers. The others had to do with kind of the state of the profession and things that we want to make better about the community. There were 614 pages of the final report. I did not read 614 pages. So I can answer a lot. I can't tell you all about all 614 pages.
What was that page?
No. So and there were kind of 13 panels. Most of those were science panels, and then there was one sort of state of the profession panel. And a 20-member steering committee. Something that's super cool is the two people who were in charge, Fiona Harris and Rob Kneiker were in charge. Rob actually is a professor here. His office is right above most of ours. So that's super cool. Sorry. So one of the things that gets decided with this decadal survey is what the next big telescope, like big flagship mission for NASA is going to be. So you'll get a lot of familiar names that were in past decadal surveys. In the 1970 decadal survey, which came out in 1972, that's where Hubble came up. Also the VLA. 1980 had Chandra. Year 2000 had JUSD, which is going to launch soon. Everybody knock on every piece of it that you can. And then 2010 had what's now called the Roman Space Telescope, used to be called WVERST, and the Vera Rubin Observatory, which used to be called LST. So all of these like really big missions get their start by being the top recommendation in the decade survey. This cycle, there was a call for proposals, and there were 4 kind of big missions that were decided. You had LINX, which is kind of an X-ray telescope. HABEX, which was dedicated basically specifically for exoplanets. LUVOIR, which stands for Large Ultraviolet Optical Infrared. Yeah, there we go. Which was big. It was going to be by far and away the largest space telescope ever at 15 meters. Hubble is 2. Yeah. And then Origins, which I don't know much about because it was kind of the 4th child. All right. So who is the decadal survey for, right? There's kind of 2 buckets of people who the decadal is specifically geared towards, in addition to just like setting priorities for the astronomy community at large. There's funding agencies. So mostly this is for the National Science Foundation and NASA, and then a little bit the Department of Energy. Setting priorities for those, basically saying, hey, we the community have gotten together, and this is what we care. This is what we want you guys to fund. And then obviously you also need Congress as a big player, and the Office of Management and Budget, etc. Basically, the gist is in order so it's not like whatever the head of the House Science Committee, whatever their favorite astronomer wants to be built. This is more of like a community exercise that then when people are advocating for funding, you can point to the decadal and be like, hey, we went through this really long process. We ranked the things that we want to do. Here's what we want. Here's what we want funding for. And so this is a group of astronomers, I think this is 2018, that actually went and did that basically, lobbied Congress for, hey, this is what we want to have built. Many in the audience will notice our own Darnik Ajadi. So that's super cool. So one of the big things that the decadal is used for is advocating for this one. So I talked a lot about what the decadal is and why it matters, and so now we're actually going to talk about what was actually in the Astro 2020. So there were 3 big major science names that came out of this. And they all have really fancy names. So pathways to habitable worlds, basically just we want to find and characterize as many exoplanets, specifically Earth-like planets, as we can. New windows on the dynamic universe. So using new techniques, new ways of discovery for studying the most ridiculous and amazing events. This is a direct imaging of a black hole, for example. And then unveiling the drivers of galaxy growth. So how do galaxies, like really nailing down, how do galaxies form? How are they connected to the cosmic web or the gas that's around them? Really nailing down that process. And that all ties into kind of, how did we get here, basically. So we recall this slide of the proposed missions. So the decadal looked at this awesome menu of observatories and kind of gave both of these telescopes the side eye. And when 2 telescopes love each other, sometimes another one emerges that's the best of both ideas. So the next flagship mission is a combination of basically HABEX and LUVOIR. You can kind of think of it as Ultra Hubble. That's how I've been sort of thinking of it. So it's an all-purpose infrared optical ultraviolet observatory with about a 6 meter with about a 6 meter mirror. That's 250% resolution and 6 times the light gathering power of Hubble. So a really big deal. It should be It's slated to be ready to launch by 2040, and it'll cost about $11 billion. So people will kind of look at this, ready to launch by 2040. And with a great tweet, the most jarring part of Astro 2023 personally is realizing that according to this chart, I'll be in my 50s when getting before launches, which really set that into perspective for me. I will also be in my 50s when this happens. And it also led to my best performing tweet among astronomers ever. So you'll notice if we take all the words that are in here and kind of jumble them back around, you get boudoir. And this seemed to be pretty intentional on the behalf of the decadal committee. And so I said it's only a boudoir, it's from the Loire Valley in France. Otherwise, it's just a sparkling large infrared optical ultraviolet. So that was good. That was really good. So in addition to this selected project, as merge between the best parts of CAVX and boudoir, basically. There's also this mission technology and maturation program. And the basic gist here is that flagships take about 20 years from when they're conceived of to when they're launched. And they're often, at least in the past, have been greenlit with unproven tech, basically. And this was something that kind of plagued all four of the missions that got proposed. Each of them had something that was like, oh, I don't know if we can build that. And this leads to delays and cost overruns, looking at James Webb, but also all the other ones. So starting now, basically, with this proposed maturation program, the tech needs to be proven before you build the telescope, is the idea. Which sounds like there might be some engineers in the room going, well, duh, but we haven't done that yet. And to accommodate for this and make sure that it's not like it takes 20 years to build a telescope and then we need to just do 20 years to build the next one. They also have this idea to basically design things in parallel. So once one flagship gets greenlit and construction starts happening, you start designing the next decade's one in order to kind of avoid gaps and make sure that we actually have at least a couple of these things going on in orbiting Earth at once. Okay, so that's all space telescope stuff. But also, there's some really cool ground-based stuff going on. So the biggest telescopes ever. So this is kind of these two telescopes have kind of jointly been referred to as the AoT project, extremely large telescope. Naming, yep. So GNT is Giant Magellan Telescope, TNT is 30 meter telescope. The idea here is that basically the biggest mirrors, the biggest telescopes are built on the ground. And currently, world-class mirrors are 8 to 12 meters. And these projects, which are both proposed right now, would be 25 to 40 meters. So 100 times the that. The recommendation for NSF was, hey, the US really needs to get in on building these really massive telescopes. And so the NSF should fund 25% of both telescopes or 50% of only one telescope for a total cost of around $1.6 billion. This will help the US kind of catch up to Europe, but there's actually considerable hurdles to go. GMT has a mountain that they're building things on, but has not secured all of its funding, even with this 25 to 50%. And then TMT has the same sort of funding problems, and they don't know which mountain it's going to go on. So that's something that needs to get figured out. And the decadal survey was just like, we don't really care which among these it is, but both telescopes kind of need to get their act together so we can decide which one. There's also a whole bunch of kind of next generation recommendations that are either like co-funded, but would be co-funded by NSF and some other departmental agencies, or they're just saying, hey, we think this is a really good idea and we should go with this. So CMB S4 is a ground-based radio. And basically the idea is you have this possible microwave background, Cosmic microwave background, and it'll look at the polarization of that light to detect the imprint of the early universe on that. So like gravitational waves, but in the CMB, which is pretty cool. The next generation VLA, which is a artist conception of that there, is going to have the resolution to see planet formation in action, happening at like live. IceCube Gen 2 got some love, and so you have really high energy, that'll help detect really high energy neutrinos from extreme events, like binary neutron star black hole mergers, type of thing. And also, they talked about upgrades for LIGO and tech development for LIGO successor, which you can kind of think of as LIGO in space. That's the thing right here. And so, like, all of this stuff got kind of a very positive review from the decadal. And if I'm putting everything on one slide, this is the one slide that everything goes into. So we talked about these main science topics right here: the pathways to habitable worlds, windows of the universe, the galaxy growth, forging the frontiers. This is where they're talking about like, hey, we should build these next-gen space telescopes, have this maturation program, the US ELTs, etc. And then they actually did a really good job of emphasizing kind of the foundations that are going to be based on the community. So things like expanding the amount of funding for grants, bringing back NASA used to have kind of theory-based grants for astronomers, and those went away. They said, hey, bring those back. We need theorists to help interpret these observations. Increasing diversity, advancing crucial laboratory measurements. Basically like everything got thrown into this decadal. And so, which led to this great tweet. My quick reader answer 2020 is basically, let's do it all, it's great. Which I think is a pretty accurate summary. Now, some of you might be thinking, geez, Alex, all that sounds pretty expensive. And you're not wrong. We're talking like each of those things that I just said are a couple $1 billion at least. And so these are kind of old, but I still like them a lot. So this is looking at the cost of some things. You have telescopes that got proposed. This is like the full funding level that got proposed when these telescopes were suggested, so links, origins, etc. The amounts in $100 bills that the U.S. military lost in Afghanistan in 2012 is there. The cost of air conditioning U.S. military bases in Iraq and Afghanistan in 2011 is that chunk. So like these are expensive things, but in the context of things that we and the U.S. government funds, they're not that big. And we can play this game a little bit more. So U.S. consumer annual expenditure on credit card late payment fees, that will sliver. And then like we just put the annual Pentagon budgets. Come on. And so I would argue that this decadal basically put forward a realistic but very compelling and across all wavelengths awesome suggestions that are big, bold, and exciting. And now it's time to work. Basically, astronomers need to back the decadal and make those dreams a reality. So I have some credits here so I don't get in trouble for using the Google Slides template that I used. And I can take any questions.
So, you mentioned that some of the newer telescopes are, so much bigger than the older telescopes, and then you said they got a certain amount of increase in light gap factor. And I'm doing the math in my head with the numbers I'm giving. I'm way off. So, like I thought it was like you just like square the ratio of the linear The size. You square the distance of the size. No. I think you understand my question.
Yeah. How does the size relate to how much light? Right. So the question is, how does the size of the telescope relate to how good the telescope is? And I threw a couple numbers in there that might have been useful. I don't build telescopes, so I'm kind of wheeling in here. Oh, Taylor.
Really good gauge, like, so what you can do in 4 hours, like, your telescope, you can do 4 minutes in the 30-year telescope.
Yeah. So basically things scale. It's also how much time you're spending sitting staring at the telescope. One kind of interesting thing is that there's a lot of engineering challenges to kind of quadrupling the size of your mirror. Things like as the mirror tilts, as it's observing parts of the sky and tracking with things, the gravity of the mirror warps the mirror, and astronomers are coming up with ways to fix that. So there's lots of like other concerns, more real life than just like the light gathering power squared or whatever.
Why is it more than the size squared? Like that's so much. The factor of 60 by increasing the size by factor of 3. That's wild.
We'll talk, but we'll talk there. There's a lot of people in the audience that can work through this better than I can. Sarah.
Rowan actually has a question.
Rowan.
Rowan wants to know. He's telling you.
You won't look, it's okay.
No one's looking.
Look away.
What do you mean by the offices on top of the building? There's some.
Oh, no, okay, yes. So I was talking about Rob Kennedy's office in relation to everyone else's. So I'm sorry if I said top of the building. So all the grad students who are here, our office is on the 3rd floor of a building on Texas A&M campus. Rob Kennedy's office, one of the guys who led the gate, is on the 4th floor. That's all I'm saying.
That's another part of this. When you were talking about the ground-based telescopes, you said that they were asking the NSF 25%, which funded your percent?
Great question. So the question was if NSF funds 25 or 50% of the extremely large telescope, the ELTs, where does the other funding come from? And the answer to that is sometimes it comes from institutions themselves. So Texas A&M bought a chunk of telescope time, and that was some contribution in terms of money or building things for that. And then also countries can also buy into these projects. And so one of the things that the scientists are doing right now is going around to different countries and consortia institutions and individual rich institutions and being like, hey, we need money to build these things. So that's it. It's kind of a hodgepodge of all those places.
So
why are they not? The question. Okay. Why are they not asking the NSF for more? The idea there is that if you look at where the scientists come from that use this telescope time, about 25% of it is US based. And so it's pretty fair to ask the NSF to fund about 25% of the time. Taylor.
So for the telescope concepts that weren't supported in the field, do you think so much?
Right. Okay. So talking about telescope that didn't get suggested in the Gale. So specifically for the space missions, I think there's probably still hope there. So one of the we talked about how they say in parallel when you start building one flagship, we're going to start planning the next one. The decadal here gave a suggestion for what the next one is. So there's this Ultra Hubble thing. That's the suggested one for this decade. And then they gave a soft suggestion to do a large X-ray telescope the next one. So that would be LINX, which was another on the one that was over there. Because all four of those telescopes covered most of the science goals and most of the wavelengths that we would try to do in space, each of those was a pretty good representation of what we want to do anyways. So if it's an X-ray telescope, yeah, that is probably going to look something like LINX was proposed to do. Chris.
So when you listed like some of the previous titles, you had like 70, 80,000. What happened in 1990?
Yeah, so the question was, I listed a whole bunch of the decadal proposals, and I skipped 1990. Very, very good observation. In all honesty, 1990 had recommendations, but they weren't like famous like to this audience. And right now it's escaping me what it was. But this is something that you can find on like really easily. But basically, there was Hubble, Chandra, JWST, and then like something that no one's probably heard of in this audience. So I skipped it. Rowan. Rowan asked, why aren't we doing trivia?
Does John know why we're not doing trivia?
And I'm gonna table that to the MCs. Yeah, that's one.
The 1990
All right, so the 1990 decadal recommended Spitzer, which has been affectionately referred to me at least, as a trash can in space. So it's a good trash can. It's a very useful trash can. But that is how it's advertised. Also, I think Spitzer died. I think it was the earliest great observatory to go, and so yeah, it didn't have a very long runtime, anyways. So this gets back to why I skipped over it. Sylvie.
What are you most excited about from the telescopes that are launching? Or are you just happy?
Okay, question was, what am I most excited about? So from this, I'm very excited that the decadal, kind of like I said, went bold. It's very hard to pick something that got proposed, that was kind of bubbling around in the community that didn't get a call out in the decadal that said, hey, this should be funded. So I'm excited for that. They went bold, but it's also realistic, and it's going to be very easy for astronomers to go to Congress and be like, hey, this is this is one of the most fleshed out plans that we've ever done for this. We think this all this stuff should be funded. So I'm excited for that. As far as like literally my favorite telescope for my science, I'm really happy that they didn't scrap the idea of a US ELT. That's going to be very, very useful for observations of things that I want to do in the far future.
Thanks, so next up is dark matter within the news.
I can go all the way back to it. Oh, yeah, sorry.
What's up, everybody? How are we doing tonight?
Hey, you look a lot like the last guy.
Yeah. All right. So we're gonna talk about the news. You all know what this is like. Astronomy headlines. I'm gonna try to explain what's going on. So first off, the decadal happened, but we just talked about that. So ooh. So that was fun. That was spicy. All right. So darting an asteroid away. So this was actually today that this popped in my New York Times feed. So that's the thing. So the idea here is, I'll skip to here. So in 2005, Congress told NASA basically to protect us from asteroids that come flying a little bit too close, or might hit us. And so to sort of test whether or not we have the technology to do that, NASA is basically launching a test case. So there's this asteroid called Dimorphos, which is artist illustrated right here. This is very faint. The thing, so the idea here is basically what NASA wants to do is launch something. It looks like a telescope, but it's not actually a telescope. And basically smash it into some orbiting thing. So an asteroid that's going to hit us. That smash changes the direction of the orbit, so then it doesn't hit us. It's the basic idea. So this is testing out that theory with this asteroid called Dimorphos, which is not actually super large. It's actually in a asteroid system, and it's the smallest of that. It's only something like 5% of the total mass in that system. But they're smashing a 1,200-pound satellite that's the size of a refrigerator into that to see, hey, can we actually move this thing? Very important here. Crucially, no one is in danger from anything going on here. Dimorphos isn't going to hit us. It's not planning to hit us. This is just the one that they picked to see, okay, can we actually make this happen? So yeah. So if you see anything about that, this is what's up. We're testing our capabilities to do this, and nothing else is going to happen. Yes, Rowan. What's it gonna hit? Well, right. So this is actually important. So we're not trying to break apart the asteroid. All we're doing is nudging it so it has a different orbit. And so
We're gonna control it, like we're gonna control it.
we're
Like,
gonna
it's gonna stay solid.
we're gonna find out. If we're gonna find out if we're gonna control that. Right? So this is the first time people have tried doing this. We have launched kind of probe missions to land on an asteroid, grab some stuff, and bring it back here. We've done that before, so we know how to hit an asteroid. But this is the first time that we're trying to actually change its orbit. So yeah, so very crucially, we're not trying to blow it up. We're not trying because then you just have a whole bunch of pieces flying out instead. But this is actually giving the thing a nudge so that the orbit changes, so it wouldn't hit us if it were going to hit us. It's going to hit us.
Have you seen these effects?
I don't think so.
I know.
Okay, more gravitational wavelengths. More. So there's a collaboration of gravitational wave observatories. If you've heard of LIGO, that's in here. Virgo's in Europe. Hagura is Japan. And so basically, all of these observatories are detecting kind of distortions in space-time, basically, that result from two very big compact things. So think like two black holes merging together, and that generates all these things called gravitational waves that propagate through, hit us, and then are detected by LIGO. So these guys just finished up their third operational one called O3, and just published the result from that. And so we added 35 new mergers to the catalog of the growing list of black hole, and black hole neutron star mergers that we've had so far. There are some really cool things in here. So one example is a black hole eating what we think is the smallest neutron star that we've ever observed, basically. So that's really cool. And another one possibly had two black holes that spiraled together and merged, and the result was something that's about 100 solar masses, which is a really interesting number, because if you kind of look at the distribution of black hole masses, there's really small things that are few solar masses, and then there's really massive things like at the center of galaxies. In the middle, we call intermediate mass black hole, IMBH. And we haven't found those yet, or we haven't found many of them. That's a little weird. And so possibly we found one, and this would be a mechanism for how to form those things. So that's neat. And then the fourth operating run, 04, should start in late 2022. After a really nice upgrade. I can't still tell you what they are upgraded, but all of the articles that I read were like, yeah, it's good. Hurts.
Did they see the optical counterpart function any of these?
Right. So the question was, we saw these gravitational wave events. In the past, we have seen, in addition to the gravity waves, we've also had other sources, namely like spark of light that came from the same direction that we think is associated. Most of these were binary black hole mergers, so we don't get light from any of those. Now, if I remember correctly, some of them were black hole neutron star mergers, and I have no idea if we found stuff from that. John,
Are we predicting like the same, like how do the number of black hole neutron star mergers, neutron star, black hole mergers stack up to our prediction of
right? So the question was, we're starting to track many of these things as opposed to one that we had in 2016. So we can start talking about how many of these things should we be expecting given our models of how black holes form, how galaxies evolve, etc. And are those lining up? I don't know, but I think we're starting to get to the point where we can at least try to check that. Rowan has a question. Oh, hi, Rowan.
Say it again. Will you tell us next month? Will you tell us next month?
Well, tell us next month if it works.
Yeah.
Oh, no, will you tell us next month, because you said, something was gonna be written in the, article?
Oh, yeah, I definitely will. We said that. All right, last one. So, galactic cannibalism all the way down. So one of the ways that we're pretty sure galaxies form at all, we know that galaxies form at all, is through the accretion and mergers of a whole bunch of smaller things. And so a really nice example of that is the Large Magellan Cloud, or LMC. That is the most massive satellite galaxy in the Milky Way. So this is actually brighter than this is a really nice image. This is actually brighter than you can see it in the night sky if you're in the south. Can't see it in the north because it's not there. So the idea here was a whole bunch of astronomers took spectra of 11 globular clusters, which are kind of really compact objects that have a whole bunch of stars in them. And the idea behind taking the spectrum was to study their chemistry. So from that spectrum, spreading the light and measuring how bright things are at wavelengths, you can actually figure out things like, okay, how much iron or nitrogen or oxygen are in these globular clusters, basically. And the cool thing here is that 10 of them looked exactly the same and match the chemical properties of the Large Magellan Cloud, like nothing particularly different. But one was very, very different. And the idea there is that instead of coming from the LMC itself, there was a smaller galaxy that the LMC merged with at 8, and that one globular cluster that's an outlier is actually from the original galaxy, and that's why it has a different chemical history. So that's why it's galactic cannibalism all the way down. I don't think I had a fun thing. I think this is just so sorry. I was really tired today. So yeah, that's what was in the movie. Now I'm done. I'm not gonna talk.
So if you have questions, you can ask him, but he's tired. He got his booster shot yesterday. So we're gonna take a quick break, about like 10-15 minutes. So stay tuned for the next talk about space vampires and how to protect them. Talk to the astronomers, drink some beer, plus, because there's other stuff too. Let's see. Yeah, 10-ish minutes. And then, this is the t-shirt that we have. If you donate $15, you get a t-shirt. It's not that expensive. So if you want to write Astronomy on Tap and tell your friends about who we are. Yeah, and then just hang out. And we'll see you in like 10-ish minutes. And take your guard, however.
you stop the music? Do you have anyone watching?
Hello. Astronomy.
Just not gonna say how.
One second. Yeah. All right. Welcome back. For those of you who just came in, we are the astronomers at A&M, grad students mostly, and we give talks about astronomy things. And we also talk about other things like what's up in the sky, which is our next segment, by Cosmic Kid, the Cosmic Kid with a K. And yeah, don't be shy, come on up. Yaswant is the Cosmic Kid. I don't know, what's some facts about Yaswant? There's a lot of fun things about Yaswant. Woo! Yaswant! Alright, let's give it up for the Cosmic Kid.
Okay, what's up, everybody? Woo! So this is something where I tell you what's up in the sky, what's fun to observe for all you amateur astronomers and some professional astronomers who've never looked in a telescope before. Which is actually like half this crowd. You'd be surprised how many professional astronomers have no idea how telescope works, so have never looked in the night sky. But anyways, that's a digression. Let's talk about what actually is up in the night sky with the fun stuff that I recommend everyone start with. Starting off with astronomy, if you just got involved in some next set of binoculars or small telescope or something, this is also what I'm going to start with, which is about planets, which are always a pretty things to look at, honestly. So for the next month, if you look just after sunset in the southwest, you'll find Jupiter, Saturn, and Venus all in a line right next to each other, which makes it really easy to find them. They're also ridiculously bright, which also makes it really easy to find. In fact, Venus right now is the brightest it's going to be for all of 2021 and all of 2022. So this is a peak moment to look at them. If you're in ancient astrophotography, this is a great time to get some really nice photos of these planets and stuff all in the sky. And then if you look through from December 6th through the 9th, The moon is traveling along the planets. So around the 6th, the moon is going to be somewhere over here. On the 7th, the moon is here. On the 8th, the moon is really somewhere over here. On the 9th, the moon is over here. So again, if you're into astrophotography, that's a really easy way to get some really beautiful pictures. If you're not into astrophotography, you just help figure out what things are. Like, hey, Yaswant said that the moon would be here on December 7th, which means that must be Saturn. Wow, the planets. And then you can go like, I don't actually know what day of the week this is, but when you're out at Northgate or whatever, you can go point at the thing in the sky and be like, oh, that's Saturn, that's Jupiter. And all your dark friends would be like, wow. Yes.
Can you go through which one is which right now real quick?
Yes, so the one labeled Venus is Venus. The one labeled Saturn is Saturn. Oh. Venus, Saturn, Jupiter, the moon.
Is that actually the moon?
I mean, it's a simulated image of what the night sky would look like in December 7th, but that would
Wait, but is that as big as the moon is going to be?
No, so the moon around this time is going to be a crescent moon, so it's going to be actually very time sliver, which is actually really nice because that means that everything else can see. But this is just showing you the position of the different objects.
This is like this much of this.
This is like, let's see, about 4 handwidths of the sky. Yeah, so actually not that big part of the sky, so that's kind of fun. Are you leaving them or are you looking at 1 degree in the sky? All right. Well, the other fun things to look at, if you're looking at other fun things to look at, the Gemini meteor shower is one of the main meteor showers, the meteor showers. It's going to peak from December 13th to the 14th. He's coming the asteroid 1345, which is interesting. Most meteors origin from comets, not asteroids. So it's a little weird that they have this asteroid. In fact, there's so many of them in this asteroid. At the peak, they can be up to 150 meters an hour. A lot of those are going to be really faint, so you might not be able to see those, but still, this is the best bet seeing meteor from the same year. If you've got a lot of origins stored up, those stimuli should start to see, so save them up. Some observer tips, if you're interested in looking, is go to a dark site because most meteors are super, super faint. So, drive out into the country somewhere, hopefully somewhere you have permission to go, or if you don't have permission, just, dress warm and bring a blanket because this is, middle of December, it's going to be in the middle of the night, so you're going to get cold. So bring a blanket, dress warm. Also, you might want to like blank down some pictures. Again, you're going to spend hours looking at the night sky. Let me tell you, I've done meteor observing before, and spending an hour doing this really hurts after the first 5 minutes. And doing that for like several hours, it's just misery. So bring something comfortable to sit in or lay on. You're going to look in towards the constellation of Gemini, which is why it's called the Geminis, which is basically just, it's that part of the sky where the universe comes from. And so, ancient people are like, wow, Gemini, the constellation that's been giving out meteors, it's called the Geminis. And now we're like, no, it just so happens to come up like the sky. But yeah, this is also a composite image of the Geminis from a couple years ago, just so you can see over the course of an hour how many meteors are coming. And we're coming in all sorts of different directions and not a sequence like this. So you really have to like sort of be vigilant and not just like stare at one patch of the sky, so like look all around, just be prepared for that brief street. And these things go by really fast. The Geminis especially are really fast with your shower, so they're only really streaking for a couple of seconds. You really want to be prepared for that. But if you do find some, it's really beautiful. And like I said, you can make a lot of wishes on the space. The last thing that's going to what's up, this is sort of more challenging to define. The dwarf planet series is the opposition. So opposition means that this is the closest approach to Earth in its orbit on November 27th. It's located in the constellation Taurus, so it doesn't really show up too well here. So here's the constellation Taurus. Here's the bright star in Taurus called Aldebaran. And then here is where Sirius is supposed to be. So you can sort of if you can find Untitled Devarakonda on some really websites, courses, should hop from start with the series. I think easily visible with binoculars and small telescope. This is one of the things we do in our introductory astronomy labs for our students who never used a telescope before. We'll be like, you'll find this cool. And they'll be like, that's impossible. I'm like, we'll try it. They find it. And it blows their minds. And so, if a undergrad who doesn't want to be there can do it, and somebody who is motivated can probably definitely do it. Fun facts of the series is it's the only dwarf planet in the inner solar system. It's the largest object in the asteroid belt. It makes about 25% all of the mass in the asteroid belts. And it was named after the Roman god corn and harvest, and that's where the word cereal comes from. So, more fun facts to impress your friends as you walk around dropping more. And that's what's up. Any questions?
Why do the Geminis always come from Gemini?
They don't always come from Gemini. What happens is this asteroid as it goes through the solar system, it just so happens to line up so that when it's traveling through past the Earth, the point that it's flying at is next to Gemini, basically in the sky. So the meteors see coming from Gemini.
And it happens every year.
Yeah, it happens every year. It doesn't always happen at the same rate every year because sometimes it doesn't perfectly overlap, but for the most part, yeah.
Are these in orbit? Like, or are these the asteroid constantly rotating?
So think of like something that was destroyed and it's shooting in the direction, and the Earth is moving as we go around the sun. The Earth is moved into a position where it's so we go away from it, but they're still shooting off the debris.
Still?
Yes. So the Geminis were originally observed a couple of hundred years ago, which is when they were first observed, and it's been slowly picking up pace ever since. I think it peaked off the Earth's because it's like, several trillion tons of material.
Yeah, also stuff traveling more distance, yeah, right? That distance takes a while to go distance. But all of this material traveling all of this long distance, you can make this happen.
So are we seeing stuff that we could have seen like last year, but then it just went around and then came back? Or is it all brand new stuff?
When you see a meteor shower, that's the stuff right in the Earth's atmosphere. So it's right. So at this point, it's just us passing back through to church and everything else that you get.
I can explain more in depth the operating one.
So what happened in this asteroid caused this?
We don't know. Most likely it was collision. Most of these things would be either collision or the comets, especially as it passes close to the sun, parts of them will break off as they sort of melt onto the ice. So parts of it will sort of melt off, and then we'll trail it behind, and eventually, as they pass through the Earth, they will sort of fall into the Earth.
So, okay, one more question. Everything's orbiting the sun, right?
Everything in the solar system.
The solar system. So why is this debris always in the same spot when we come around to it? Why is it not also rotating around us in a different location? But it is.
Well, it's so all the debris is following this asteroid, and then every now and then, because of as it sort of gets closer to the Earth, some of the debris will be falling into the Earth, and some debris will be on the asteroid.
So is it just something that's like close to our orbit? And
Yeah, imagine just like a really long conical tail. So we're only grazing the edge like all this, but that tail spread over millions of miles. And because there's not even space that it interacts with until it gets closer to the space. Thank you, Dr. Kid.
So next up, we have Addy Evans telling us about space vampires. Addy is a third year Third year grad student, now a PhD candidate. And fun fact about Addy is she is a real life vampire. So she's going to tell us about her own.
This is for all my vampire friends that couldn't be here tonight. Okay. So, yeah, like Justin said, I'm Addy. I'm going to be talking tonight about prospects for detection of space vampires. Okay, this probably seems like a little out of left field, especially because it's not October anymore. So I'm going to show you guys the comic that planted the seed in my head about how could we actually detect space vampires. So you can see this guy says, yeah, I made the first telescope without any mirrors in it, and he looks in it, and there's a bunch of space vampires, because vampires don't have reflections, I guess. So yeah, I started thinking about, like, can we detect something like a space vampire? I mean, obviously, I've never met a vampire or a space vampire. I don't know about you guys, but we can, make some assumptions about it and see where it gets us. And I also wanted to do it for everyone here today because it's kind of an introduction to kind of, in general, how an astronomer thinks about how to detect things in outer space. So it's kind of an introduction to that sort of thing. Okay. First of all, let's talk about this panel. Okay, so he says, finally, I made the first telescope without any mirrors in it. So he looks like he's wearing, he looks like he's wearing kind of like a modern lab coat. And so unless he's a time traveler, which he's looking at space vampires, so like maybe he is. This is just wrong. I mean, so the first telescopes that we think of in a modern sense, where there's like a lens or whatever that we look through and look at stuff. The very first one was in like the 15 or 1600s by Galileo-ish, I think. And it was a refracting telescope. So it didn't have a mirror in it. So like one of the very first telescopes ever did not have mirrors. So I just want to point that out first of all. It's like they completely forgot about refraction. And so I'm going to briefly talk about refracting telescopes and reflecting telescopes. So first of all, refraction is this idea of you have a lens, it's curved in some way, and light goes through it, and then because of the curvature of the lens, converges to a point where the image forms. This is basically how binoculars work, except binoculars have like a few extra gizmos in them, like a lens that also magnifies that image, but you can think of it that way. So that's kind of what a refractive telescope does. And so yeah, so I just need to point that out first before we talk about anything else. And so then let's get to the differences of a reflecting versus a refracting telescope, because my main question from that comic is, can we actually use refracting telescopes to detect space vampires? So let's go over the difference between refracting and reflecting. Also, you might want to play a drinking game where I mess up the difference, or I mess up saying refracting and reflecting. But yeah, okay. So there's a couple differences we can see on here. Of course, the reflector is just useless to us because it can't see vampires. So what's the point of it? What's the point of anything if you can't see a vampire? And then the refractor, on the other hand, even though maybe theoretically speaking it can see a vampire, it has its own issues because refractors are generally more expensive than a reflecting telescope. Like the biggest and best telescopes in the world that we have are of the reflecting kinds because it has a mirror. And if it's a mirror, you only have to worry about one side of the lens as compared to the lens like in a refracting telescope that the light has to travel through. So it's cheaper in that sense, and also in the sense that since you only care about one side, you can put in like a lot of infrastructure to hold up the mirror. Whereas if it's this clear lens, you have to hold it up on its sides, which you can imagine just doesn't work very well. So reflectors are in general like better telescopes. But with that being said, let's give it a shot. So okay, so I did some Googling, and the largest refractor ever built, I think, is this 40-inch aperture at the Yerkes Observatory. I hope that's how you pronounce that. So again, can we use this to detect space vampires? But before we get to that, actually, so I did this and then I was like, wait a minute. A better question than that is at what wavelength does Vampire radiation peak at? Because ideally, if we've never seen an object before, we want to choose a telescope that is best suited to look at that object. And that means we want something that's best suited to look at where the radiation peaks at, because it's going to have the highest flux in that case. So here I'm showing the electromagnetic spectrum. A refractor, generally, I think almost always, but it's scary to say always, so generally, is best for looking in the visible regime. And so we can actually do a nifty, just little calculation to figure out where a vampire's radiation peaks at if we use this thing that we all just love so much, called black body radiation. So I'm not really going to explain what it is. Just know it's beloved, and also really its usefulness to me in my life experience is that you can use it to approximate this radiation peak, with just the object's temperature. And so that's really the beauty of black body radiation. And we're going to use that today with this equation, which is called Wien's Displacement Law, a result of assuming black body radiation. And you can see this lambda max here is that peak wavelength that we're talking about. And it's equal to a constant, which you can do over the temperature of that object. So we're going to do this calculation, but there's one important thing that we need for this calculation, and that is the vampire's temperature. But what is the temperature of a vampire actually?
Less than human body.
Less than human body temperature.
More than
2 Kelvin, more than 0 Kelvin. Okay, that's more than science.
Okay.
We should talk later. Okay. So yeah, great answers, everyone. A+. Here's my thinking. Okay, they're in space. Who knows how close they are to other things that cause heat or whatever. So who knows? I think so. Let me start over. Okay, so I think the reason I've never met a vampire. I think the reason that they're cold is because they're undead. And so they don't have all of those metabolic processes happening that keep us at a very specific body temperature. And so I think they could reach thermal equilibrium with in whatever environment they're in. And so I'm thinking, okay, they could probably get pretty hot. But let's assume, for the sake of needing to calculate something, that vampires were people once, or they're space vampires, so they were space people once, and let's assume that those space people / were pretty similar to us. They had human-ish skin. So in that case, the human body begins to sustain burns at around 120 degrees Fahrenheit. So my thinking is they don't really care how hot they get, but it's probably really annoying to have blisters. So that's my thought process with this maximum temperature. And then let's take the funsies if we want to calculate a lower temperature in that case. Again, with the thermal equilibrium argument, but they can get as cold as the ambient temperature of space, which is 2.7 Kelvin or around -550 degrees Fahrenheit. And so that's the lower limit. But to do this calculation, for now, let's focus on this max temperature, because that will give us the most radiation and the most energy. So if we just plug this into Wien's displacement law, lambda max is this V over T, and we know that this constant is 2,898 microns Kelvin, and we have our very scientific, well-motivated temperature of 120 degrees Fahrenheit, which is about 322 Kelvin. We plug that in, we get about 9 microns. This makes sense, because this is this checks out with what I know about vampires. Because we basically just said, what if a human was a little bit hotter? And humans peak in the infrared, right there, which is about, yeah, we do, which is about 9 microns. Okay, so that is, so that's what I'm rolling with. Okay, we made a lot of assumptions along the way, but we're gonna roll with it. So 9 microns, but so then there's a problem. And that problem is, refractors are not good for looking at things in the infrared. So as far as that comic is concerned, I call bullshit. Unless it was like tornado out of window or something. Then like fine, okay, sure. But we want space vampires, not backyard vampires. So my question is, can we see space vampires with other kinds of telescopes? Introducing the NIR cam on JWST, the premier infrared camera. So for those of you who don't know, JWST, as soon as it goes up, knock on wood, everyone right now, as soon as it goes up, is going to revolutionize the field of astronomy. So I'm going to see if we can detect space vampires with this bad boy. Okay, so first thing to note, this instrument is sensitive to wavelengths of about 0.6 to 20 microns. So we're in clear. And on top of that, because remember we did 9 microns? Yeah, okay. And then on top of that, we can define a lower limit on the temperature of vampires based on the sensitivities of this instrument. So just rearranging Wien's displacement law, we can calculate the temperature knowing the peak wavelength, and we get about almost negative 200 degrees Fahrenheit. So now we're doing something really interesting with this telescope, and that's probing a particular range of vampire temperatures. Probing a very discrete range. So put that in your back pocket for your next JWST program. All right, so here's our cool range that we're doing. Another thing that we should know about this telescope is that it has an angular resolution of about 0.01 arc seconds. So I put this little cartoon here just to explain very briefly that a lot of times astronomers care about the angular extent of something on the sky. So it's not the, I guess, intrinsic size of the object, but how large it appears in the sky. And so you can see here, the moon, the radius, all the velocity described at some angle. And another thing that this points out, which y'all probably can't see very well, so I'll just say it. Arc seconds are pretty small. Let's see, what is it? 3,600 arc seconds are 1 degree. So this is some pretty good resolution. So that's what we're working with. And so then my question is, at what distance could JWST see a human-sized space vampire? So how far away can JWST resolve a space vampire? And we can use trigonometry to figure that out. Okay, so here's my thinking. We already said that space vampires, I don't say human vampires, space vampires have human-like skin. So let's also say that they're about the size of a human. So I'm just going to say they're 6 feet. Okay, so let's break this down. Okay, so we're going to say this length is like 6 feet. We want to know how far away it can be from us, such that this angle is 0.01 arc seconds or greater. So the maximal distance that vampire can be away from us, such that we can resolve it. Okay, so plug in numbers. I get a distance of about 22,000 miles, which kind of sounds like kind of far. But then again, the moon is 250,000 miles away, so we're still talking pretty close. And then some of the satellites that orbit Earth are around that range too. So on the one hand, they have to be pretty close for us to resolve them. On the other hand, there could be vampires not even the distance to the moon, and we can't resolve them with JWST. Now that's what I call spooky. Okay, so another thing though about that is it's actually a little disappointing because I would think if they were that close, we probably would have already seen them. I don't know, on the ISS or something, floating around having a ball on Halloween nights. And so my next question is, at what distance could JWST see a space vampire conglomerate? I'm talking huge density of vampires, just like a cluster of vampires. Or conversely, another way you can think of this is a giant space vampire. So let's calculate that. Oh, but actually, I forgot about this. But first, so we can just throw in random sizes of space vampire conglomerate or random sizes of giant space vampires, check stuff out. But I think we should start somewhere else, actually, to get a little bit more, I don't know, science out of this. And so my question is, before we go on to any more calculations, is where would we expect to find space vampires based on their environment? And then how far away are those environments, generally speaking? And so then in that case, how big does the conglomerate or giant space vampire have to be for us to resolve it, right? Okay, so guys, here's what I think. I thought about this long and hard. Okay, so we all know vampires don't like sunlight, which is just starlight. And so let's just assume all starlight. They just hate it. So I'm thinking cosmic voids, places where there aren't a lot of galaxies or much of anything going on. Maybe all the vampires are hanging out there. And then I did some more Googling. And I found this thing called the local void. And I just think that's an excellent place for vampires to hang out in. And so it's not a cosmic void on this scale, but it's nearby. You know, 75 million light years away, nearby. And so I wanted to see how big do they have to be there. Okay, so this is kind of the same calculation. Instead of what we solved for last time. Instead of solving for the distance, we're solving for basically this side of the triangle, which in my heart is the size of the space vampire conglomerate. And so I calculate a conglomerate size of 3.63 light years, such that JWST could resolve it if there was a conglomerate hanging out in the local void. That's scary. That's huge. Like, it would take, yeah, I don't, like, that's just huge. So I was like, never mind, let's try something else. Let's try something a little bit closer. Have you guys ever heard of rogue planets?
Yeah.
No? Question mark?
Okay, getting some notes. Okay, a rogue planet is a planet that does not have a star. It's just on its own in the world, or universe, I should say. And so, I think that would be a fantastic place for vampires to be, because they don't have to worry about any nearby star coming out all the time and bothering them. And so I did some more Googling, and I found out that the nearest rogue planet is known so far is about 13 light years away. And in that case, we get a conglomerate size or vampire size of 20 light seconds, which is about 3 million miles, which is still terrifyingly huge. So I don't know how to feel about my results. Like, my own science scares me. It gives me nightmares. So that is what I have so far. So don't laugh at me. So this field is still very new. And I at this point, there's not very many of us working on it. The conferences are so small. So if any of y'all are interested in getting involved, please email me. My email. No, the Cato didn't mention us. I know, so rude. They just don't see our vision, you know. And so I want to entice you all with some future work to get you interested. So firstly, what if vampires sparkle? So I mean, that raises a lot of questions in my mind. Like, does the sparkling reflect in mirrors? Because like, I think the main reason that vampires don't reflect in mirrors is because they don't have souls or anything like that. But then, I don't know, it doesn't make any sense. This needs further testing. And also, how luminous is that sparkling? Could it make it very, very easy to detect as compared to just the faintly glowing infrared vampires? Like, I don't know. And then lastly, vampires as dark matter? What if vampires are the mysterious thing that make up 80% of the matter content in the universe that are holding all of our galaxies together? What if they're using their vampire strength to just... Thank you for listening.
this still be able to affect the gravitational lens?
So yeah, I was, oh yeah, so John asked, if vampires are dark matter, would we expect to see gravitational lensing from them just existing in space, basically, right? So yeah, I was kind of wondering this too, because okay, so here's the thing. The reason why most of us, or it's kind of been ruled out that dark matter is not some macroscopic object, is because we don't see enough gravitational lensing events. So really, this is maybe not my best work. But you know, like, we can't deny the mysteries and magic of vampire physics.
Could there be micro vampires, basically? Or nano vampires?
Humans, see, here's the thing though, because like, if it was human sized, we would need enough of them to do all the stuff that dark matter does, like pull galaxies together. So yeah, I mean, I don't know. I'm not the biggest fan of this. I'm not. I think maybe if they have like some sort of magic to them, but I mean that's a horrible answer, but that is my answer. Exactly. Okay, Curtis.
AWSC, your.
No, okay, but here's the thing. Here's the thing. Oh, Curtis says, doesn't JWST use a mirror?
Yeah, and you're made out of gold.
So here's the thing. We know that vampires don't have reflections in the optical. We don't know if they have reflections in the infrared or not. Yes.
Because also the thing for don't reflect in yours, a lot of your hair is still there.
Maybe.
I don't think.
It's gold. Okay, the JWC here is gold. Maybe we can just use it to find vampires in the ocean. I don't know. I mean, we're gonna need some heavy duty telescopes. Yes.
This radiation space.
Yeah.
So it's this radiation to if they have skin like vampire skin, right? Wouldn't they create this without heat? So wouldn't they reflect either way out?
Well, so I'm sorry, I don't understand the question entirely. I'm sorry.
So I was just thinking about what you were saying. So if they're in space,
Yes.
and space is filled with radiation.
Yeah.
This is like radiation generates heat.
I mean, so actually that's a good point because you know, like for example, like astronaut suits. Yeah. So for example, astronaut suits, like they need to wear protective gear to protect themselves against like cosmic rays and stuff. I can only assume that the vampires might be that advanced as well. Yeah, they were wearing suits. We don't know exactly how those work.
They're already dead.
I will say that my point about the history was more just they can probably withstand higher temperatures than that. I would have to guess, but like I don't know. I would in my head vampires are kind of vain and they don't want blisters.
I went down the rabbit hole when you were mentioning that. Very bad.
Yeah.
But if that radiation is coming from sunlight, then wouldn't they just like evaporate or whatever vampires do when they see the sun?
Well, so the radiation can travel pretty far, so they don't necessarily have to be that close to the sun. And on top of that, cosmic rays in particular are extremely energetic and could probably be pretty freaking painful if you got hit by one. But the nature of what accelerates them and where they come from is a little unknown. So, I mean, they probably might come from exploding stars, but again, they can travel really far. Yes.
So you said that the telescope, the AoT, can only resolve up to like 20,000 miles on the side of it, right? Something like that.
Yeah.
Okay. But isn't it also separable? Like, isn't it starting up like closer to the vampires than we are, being on the surface of the Earth?
Yeah, so it is. It is. And wait, Taylor, how far away is L2? Sorry.
Yeah, it's very, very.
Oh. So, okay. The So, okay, so JWST, you're right. So Tommy pointed out that JWST is not ground-based. It's at this place called the Lagrangian 2 point, I think is what it's called, which is 900,000 miles away from Earth. So yes. So we would probably not be able to see those, but the distance that I calculated still holds. It's just not,
So we
it's
can only see L2 there.
L2 plus 23,000 or so, yeah.
Plus or minus.
Yeah, give or take.
Which is good. It's colder. So,
Farther away from the stars. Any more questions? Okay, thank you guys.
Okay, so, thank you again, Addy, for the great talk about Displacement Law, your friends, and, yeah, like and subscribe to our YouTube channel. I think it's what, tx.ag/AoT-live.
Okay, so Instagram, Facebook, Twitter, all the social media, maybe it's TikTok. That's a lot of work. So everyone has Instagram / Twitter. Go to AoT _BCS and find out about future AoT events. Usually it's the 4th Wednesday of every month, but we still post some updates there. So tell all of your friends and make them come. And then you can also go to astronomyontap.org/events and find out about all the AoTs happening around the world, because we are not the only ones doing this. It's an organization by many grad students across many universities and institutions.
Please help us support the Grand Stafford. You can Venmo at Jose-Quintana-20. And just put Stafford Tip in the description. And please don't forget to tip Logan, our wonderful bartender. Also help support us. You can come see me for donations. And if you donate $15, we'll give you a free AoT t-shirt. Yeah, just come see me. Find me and we'll.
And ask about a
Don't ask me about that. Our next event is tentatively December 22nd. It is also the 4th Wednesday in December. We'll post updates about that soon. And then come talk to us. All the astronomers have glow sticks on, including the small child that's running around. He's also an astronomer, so feel free to bombard him with questions. That's not bad. I did not protect the glow sticks well. But yeah, please come talk to us. Please ask us questions. We're happy to hang out and just talk about astronomy and whatever y'all want to talk about. That's it. Thanks everyone for coming out.
If the astronomers want to take an astronomy picture, come up to the stage. Sarah, PhD. Yaswant.